off to the side. The example off to the side is actually too easy, okay? Because it factors too nicely. That's what I'll say. But what we're going to do as a new strategy for graphing we can write it down here. This is going to be our shortcut. You can still do the table of values anytime you want. In fact, sometimes on the final exam, it is the best strategy. You're stuck on, I don't know what this graph is supposed to look like. Do a table of values. Get a bunch of points. You're not going to be wrong, as long as you don't make mistakes finding the points. But it's a very good strategy to graph. But it's usually the slowest strategy. So you like to have faster strategies, and the faster strategy is the following. We're still going to use the end behavior, but we're going to use the intercepts as key points. And we're going to look at what that looks like. So, first of all, still using end behavior, this is an x cubed. I know that it's going to look like this. There's my end behavior. How do I find my intercepts? Well, y-intercept is super easy. It's always the easiest one. Plug in 0 for x and solve for y. In this case, you plug in 0 for x, you get 0 for y. But to find x-intercepts, we need to factor. And this is one of the reasons this question is too easy, is it's too easy to factor for grade 12. They will give you a harder one to factor than this on the exam. Why is it too easy? Because there's a common factor of x. So you don't have to use your factor theorem, remainder theorem, or anything. You can just take out the common factor of x, leaving us with x squared plus x minus 6, and then it's a quadratic. Those are easy to factor. X and x, 3 and 2. The 3 has to be positive, the 2 negative. So we have 3 x-intercepts, x equals 0, x equals negative 3, and x equals 2. And the reason this is a strategy for graphing, let me just make it a little bit wider, bigger for you guys to see. The reason this is a nice strategy for graphing is because once you have your x-intercepts and your y-intercepts and your end behavior, if you draw a smooth curve after that point, life is good. So this is what it's going to look like. We know that we have 1, 2, 3, an x-intercept here at negative 3, 0. I have another one at 2, 0, and one at 0, 0, which also happens to be my y-intercept. I know my end behavior has to start down here, has to start down there and end top right. Now all I do is draw, as best I can, a smooth curve through my x-intercepts. Oh, perfect. As long as you make your x-intercept big enough, it goes through it. And that is a fairly accurate graph. Technically, I should label at least 1 point to get my, you lose a mark on your exam, a half mark. It's an E error, E9 error, if your graph doesn't have a scale. So my graph definitely has a scale along my x-axis, but currently I have no scale on my y-axis. We don't know how high or how low this goes. So I might just plug in, if I plug in 1, 1 plus 1 is 2, minus 6 would be negative 4. So as soon as I label something with a y, I now have a scale for my y as well. So I need something for my scale for my x values and scale for my y values. If the only point I labeled was 1, negative 4, I'd have a scale, because it has both the x and the y. Okay. So this is going to be this quicker strategy. If you know your intercepts and you know your end behavior, just draw a smooth curve between them all. Now I said we would also work through the example that the textbook has. You don't have to write it down because they've got all the work listed there. But this is a little bit trickier. Okay, again, end behavior is easy. It's an x to the 4 graph. So I think of a parabola, its positive leading coefficient, there's my end behavior. The y-intercept is super easy. If I plug in 0 for x, then I get 0, 0, 0, 0, minus 6. There's my y-intercept. But our x-intercepts can only be found by factoring. So we're going to need to use synthetic division or long division to factor this. Remember the factor theorem. If something is a factor, right, if one of the ones, so eventually we're going to have f of x equals something here, x, and I'm going to cheat, look ahead, what is one of the ones that works? X minus 1. So it's going to have an x minus 1. But this number here has to work into this number. Because if you multiplied all your factors out, the last numbers would all get multiplied, and they have to give you 6, which reduces your choices. Things that multiply by 6 are like 1 and 6, plus or minus, could be positives or negatives, 2 and 3, plus or minus. We don't have that many options. So you could do the factor theorem, the rational root theorem, where you plug in a number. You say, if I plug in 1 into this whole thing, I'm going to get 2 minus 1 minus 14 plus 19 minus 6 happens to equal 0. And that tells us from the factor theorem that x minus 1 is a factor. But what do we do with that? We still need to factor this. So a review of chapter 1.2 and factoring, once you find one factor, you would set up your synthetic division. Coefficients are 2, negative 1, negative 14, 19, and negative 6. I double checked that these were in descending order, and I double checked that none of them were missing that I'd have to add a 0. If x minus 1 is the factor, then I would put a positive 1 out front. Synthetic division says bring down the 2. 1 times 2 is 2, add. 1 times 1 is 1, add. 1 times negative 13 is negative 13, add. And 1 times 6 is 6. And sure enough, this is what I was hoping for, a remainder of 0. I can now write my division statement, which is the start of my factoring. F of x, my original function, is x minus 1, and I'm left with 2x cubed minus x squared, or plus x squared minus 13x plus 6. And we're not done. We have to keep trying because it's still an x cubed. And sometimes notation-wise, I see students go, since we used f of x already, call this p of x. And I'm cheating a little bit because I'm looking ahead, but I would try p of 1, p of 2, different things. It happens to be that p of 2 equals 0. So from our factor theorem, x minus 2 is a factor. And I can do synthetic division with p of x. I have 2, 1, negative 13, and 6. There'd be a plus 2 on the outside. Bring down the 2. Multiply, add. Multiply, add. Multiply, add. And again, I wanted that remainder of 0. Now I'm going to rewrite my division statement for f of x. f of x is equal to, we already found out x minus 1 is a factor. Now we found out x minus 2 is a factor, and we were left with 2x squared plus 5x minus 3. And now that we have a quadratic, now we can go to our simple factoring. Only way to get 2x squared would be 2x and x. My outside and inside needs to make 5. I'm going to put a 3 here, 6 and 1. I need a plus 5, so plus 6 minus 1. Double check if I still get the minus 3. And now I found my 4 x-intercepts. X equals 1, x equals 2, x equals 1/2, and x equals negative 3. At this moment, you might be like, I think a table of values would have been faster. Maybe I could have found 8 values in this time. But this is going to give you a more accurate graph if you find all the x-intercepts. So when we go to graph, I have minus 3, 1 and 2, 1/2. There's the 4 x-intercepts. My y-intercept from before was it negative 6? What does my end behavior look like? This one is acting like a parabola opening up. So we know that it goes here. Draw as smooth a curve as you can through all the points. Okay? I'm going to show you the right answer for a smooth curve, and then I'm going to show you what is a very typical mistake for a smooth curve. Okay? This looks, I'm actually zoom in touch, just so that we can see a little bit more. So we can see the whole thing. And I'm going to go through, here we go through, oh my goodness. My shadow's in the way. Oh well. Go through that point. That is a nice curve. The common mistake, which I'll do in a big, fat, well, maybe not fat, but I'll just do a red pen, and then I'll erase it. Common mistake is we want to connect the dots. So students will like, oh, oops, oh my goodness, like, oh, that's really bad. But when drawing a smooth curve, if you go hard to this one, it's hard to curl back and still go through this one. But whenever you have a dot, your brain likes to think that's the local minimum, because it's your lowest dot. Usually your local minimum, I gotta get rid of the red, sorry, it's so bad. Does it make sense if you have these two x-intercepts that you would think, not perfectly, but about in the middle should be where if you're drawing a smooth curve, that's about where the minimum should be, somewhere in between those two x-intercepts? And so if you made the 6 the minimum, you have a tough time of making a smooth curve go back. And if you end up going back in time and not making a function, that's definitely losing marks for shape. So we draw our x-intercepts, we draw our y-intercepts, and then we draw smooth curves. Sometimes our minimum is going to be lower than we think. In reality, I might not have even gone low enough. We could graph this in our graphing calculator to find out. Okay? But you have to wait till calculus next year to find those. Calculus is a beautiful way of finding maximums and minimums. Only way we can do it right now is with our graphing calculators or with Desmos. So if you've labeled all of your x-intercepts and y-intercepts and draw a smooth curve through all of them, you will get full marks. Questions for practice on this one? 7 and 13.